Shall we start? Okay. So today I will do a qualitative discussion of neutrino scattering with the ordinary matter, and this will enable us to understand what the important problems are as far as experimental detection of neutrino events and how to understand them. And later we will do a quantitative discussion. And in electroweak theory, it is based on the gauge group SU2 cross U1, which means that there are 4 force mediators. One is photon, and since neutrino is electrically neutral, we don't worry about coupling of photon to neutrino, though there are experiments which are looking to measure the magnetic dipole moment of neutrino. So they are actually looking to measure electromagnetic properties of neutrino, but that's a different issue. We will not go into that. So the neutrino couples only to the other 3 force mediators, and so if it couples to W plus or minus, then we call it a charge current reaction, and in the final state we see a charged lepton, and in fact that is how we identify neutrino flavors. We see an electron and we say, okay, an electron neutrino has interacted and produced the electron. We see a positron, we say an electron anti-neutrino has interacted, produced the positron, etc. etc. So in that sense, the charge current interactions are in some sense the bread and butter of neutrino in the neutrino events. But there is also the heavy neutral boson Z0, which can also mediate neutrino interactions. So if I have a neutrino interaction with a Z0 exchange, we call it a neutral current interaction. And when a neutrino exchanges a Z0 with another particle, the neutrino remains a neutrino. So in neutral current interactions, you will always have a neutrino in the final state. And of course, this neutrino escapes detection. So reconstructing the final state kinematics in a neutral current interaction in principle is impossible, whereas the charged lepton, it will deposit energy in the detector. So in principle, it is possible to reconstruct the final state kinematics of charge current interactions. So, and in each case, there are various subcases. So, subcase 1, 2 final state particles. By the way, we always assume that initial state contains only 2 particles. In a scattering experiment, there is neutrino and one other particle. So initial state always contains only 2 particles. So here you have nu L interacting with some particle. In this case, I will take it to be neutron, and course, I have to conserve charge, so this has to be neutron. Neutrino cannot that way interact with proton in this case. And usually 2 to 2 process, we tend to call it elastic interaction, but since the final state particles are not the same as initial state particles, on the other hand, masses of neutron and proton are nearly the same, and compared to mass of neutron and proton, the masses of neutrino and the charged lepton are negligible. Not true for tau, but true for electron and muon. So, this is called quasi-elastic. It is elastic as far as kinematics is concerned, but the actual identities of the particles are different, so that difference one has to worry about. Whereas in the case of neutral current, proton, neutron, electron, so this is of course elastic. And this can be neutrino or anti-neutrino. Whereas here, if it is anti-neutrino, I have to write a separate interaction. This is the elastic or quasi-elastic, and in addition we also have purely in the case of nu E, this is also possible. Nu E turns into electron, emits an off-shell W that is absorbed by electron, and it turns into nu E. This is a special case only for electrons, not for other flavors. This looks like elastic, I mean it is elastic scattering, but through charge current exchange. So this elastic scattering actually takes place both through charge current as well as through neutral current, which actually had an important consequence in the solar neutrino measurements of Kamiokande and Super Kamiokande. Because in both those, solar neutrinos are detected through this reaction. Part of it is coming from charge current, part of it is coming from neutral current, and one has to add both. But as far as neutral current is concerned, nu mu and nu tau also could drive this. So one has to take into account that nu e's have converted to nu mu or nu tau, whereas in the case of nu e, both charge current and neutral current contributed, whereas in the case of nu mu, only neutral current contributed, and you have to add these two and then you match it with the data. So that is as far as the this quasi-elastic is concerned. And how do we calculate the cross sections? That is quite straightforward. We have the low energy weak interaction Hamiltonian. Oh, there should be a gamma. And we use this V minus A Hamiltonian to calculate both the neutrino and anti-neutrino cross section as well as these elastic cross sections. Okay, sorry, elastic cross sections we can't use the V minus A. Sorry, this is a charge current. This one we can use this to calculate these processes, and directly from electroweak theory, we can write the amplitude, the charge current amplitude for this, neutral current amplitude for this. Similarly, we can write the neutral current amplitudes for this and put them together and calculate the cross sections. So, yeah.
The L in between.
Yeah, what about it?
I didn't get it.
The L is a charge lepton. This is, this should be mu L, sorry. I'm sorry. Yeah. This is the field for charge lepton and this is the field for neutrino of flavor L. Yeah, I should have. This is the correct way of writing. So, directly from electroweak theory, we can compute these interactions, these cross sections. So, in that sense, they are well understood. But what we should remember is that these quasi-elastic or elastic interactions, they occur only at relatively low energies. As you go to higher and higher energies, just one minute, put this on silent. This is sort of basic quantum mechanics, so to speak. At low energies, you have low momentum, so the corresponding de Broglie wavelength is high. And if the de Broglie wavelength is lambda, you cannot probe a size which is smaller than lambda. So, you take the size of proton or neutron to be about 1 Fermi, compute the corresponding, take that to be the de Broglie wavelength of your probe, calculate the corresponding energy, you get a number something like 200 MeV. So, if your neutrino energy is below 200 MeV, or actually more accurately 100 MeV or so, then essentially the only reaction that will take place are this quasi-elastic or elastic. And for such neutrinos, the proton appears as essentially as a point particle. But you increase your energy beyond 200 MeV, the de Broglie wavelength of the corresponding neutrino, it becomes smaller than 1 Fermi, which means it begins to see what is there inside the proton. So, this simple picture by which we write the V minus A interaction, where we assume the proton and neutron to be point-like particles, that picture no longer works. So this talk about quasi-elastic or elastic interactions, it is valid only up to 100 or 200 MeV. Beyond that, we have to consider a more complicated picture of how neutrino interacts with ordinary matter. By the way, as far as we know, electron is a point particle. So you can have very high neutrino energies, and this interaction or even the corresponding neutral current interactions of mu with electron or mu tau with electron, they are described by electroweak model even if the neutrino has some 100 GeV energy. But that is actually, as far as neutrino cross sections are concerned, the neutrino electron scattering cross section tends to be rather small. It's the proton and neutron cross sections which are larger, so that's what we have to pay our attention. And the second important process that we consider is called I hope you have studied about resonances. First, I hope you have studied about resonance in classical mechanics, resonance in a vibrating string. So, any string has a natural frequency, and if you happen to disturb the string or a spring with a force which has the same frequency as the natural frequency of the spring, then with very little force you can have large amplitude oscillations. So this phenomenon is called resonance, and for example, that is how almost all musical instruments operate. You blow or you pluck the string, and you do it so that you hit a resonance, and that is what produces a musical note of reasonable amplitude. And for example, that is how all communication operators operate. So for example, you have sort of electromagnetic waves of various different frequencies coming and hitting your mobile phone. But how come only your mobile phone responds only to something? That is because whatever signal is coming, it's coming with the resonance frequency of your phone. And in quantum mechanics, there is a corresponding phenomena. Suppose I have a potential well and I am shooting particles at that potential well. Obviously, these particles have positive energy, so to be captured in the potential well, only negative energy particles get captured. So potential well, it cannot capture those particles, but it can temporarily capture them provided the so-called equivalent to the de Broglie wavelength of my projectile, the width of the potential well is an integer multiple of half of the de Broglie wavelength of the projectile. Exactly same condition as the resonating string. How the width of the potential well? The width of the potential well is an integer multiple of half of the de Broglie wavelength of my projectile. If that condition is satisfied, then the particle tends to get partly trapped in this potential well, but eventually it comes out. And that is also called a resonance. So, what you are saying is that you are sort of temporarily you are creating a excited state of this potential well. All the bound states have negative energies, but this excited state has a positive energy. But it is a bound state of an excited bound state of the potential well. That is what you call a resonance. And it is found that it's possible to create such excited states of protons and neutrons. And these are well known. They are called delta resonances. So, what you have is mu L plus neutron. It produces a L minus plus a delta plus resonance. And here actually it need not be neutron, it can be proton also, because there is also something called a delta plus plus resonance. And we can have mu L bar plus proton giving rise to L plus delta 0 and mu L bar plus neutron. So in fact there are 4 possible resonant reactions, and then this delta plus actually can decay into 2 possibilities. It can decay into a proton and a pi naught, or it can decay into a neutron and a pi plus, whereas this one decays only into proton and pi plus. Here again there are 2 channels. There is neutron and pi naught, proton and pi plus, whereas this one has only one channel, that is neutron and pi minus. So what you have is a final state consists of 3 particles: charged lepton, a pion, and a proton or a neutron. So you can think of resonance scattering as a 3-body final state. And something similar will happen on the neutral side also, neutral current side also. And this resonant scattering is is the part which makes life most difficult for people doing neutrino physics, whether theory or experiment. And I will describe the reasons for it just a little later. But to and by the way, this okay, so similar three body final states. NC interactions also. With the final state consisting neutrino plus pion plus neutrino. Yeah.
What is the lifetime of these delta particles?
Oh, unmeasurably small. So you don't see the delta particle, delta resonance in the detector directly. The existence of these deltas is inferred you do a scattering of pi plus on proton to pi plus on proton. So you do an experiment and you plot the cross section as a function of pion energy. So the usual rule with cross sections is cross section should decrease with increased energy as E square. So you will find that when I say E pi, yeah, this is the total energy of the pion, m pi square plus p square. So you find that this is decreasing like this, but suddenly it will increase and decrease like this. And this is, in particle physics language, this is called a Bright-Wigner resonance, because Bright and Wigner described it in the first, they did it in the case of nuclear physics, but we can borrow their language here also. So this is what is C, and the position where the peak occurs, we interpret the peak due to this delta plus resonance, and the position where the peak occurs, we call it the mass of delta. But actual delta you don't see in the detector.
To some extent, this delta particle is like virtual particle. Not completely.
No. We have a technical definition of what is a virtual particle in particle physics. Virtual particle is one for which E square minus P square is not M square. Actually, more technical definition is that it is off Morse shell, but people tend to call it virtual. But that is not the case here. The delta plus is being formed, but it is formed for such a short time period. By the way, along with we can also measure this width, and based on the width, we can calculate the lifetime of the delta plus. Answer comes out to be 10 power minus 23 seconds. So, our interpretation is delta plus is indeed formed, but it lives only for about 10 to the minus 23 seconds before it decays into a nucleon and a pion. So we come back to these resonance interactions, and I mentioned this in a previous class. If you look at nuance, most of the effort of nuance and now Genie goes towards taking care of these resonance interactions properly. The reason is twofold. One, of course, is there are so many of them, and second, the resonance interactions. See, the mass of delta is about 1240 MeV, which means m delta minus m nucleon is about 300 MeV. So I mentioned that up to 200 MeV I can live with elastic or quasi-elastic scattering, but above 200 MeV I am probing inside the proton. So before I start probing it at its minute level, what is happening here is that my projectile is somehow delivering enough energy to the proton to make it unstable. So it gets excited to this energy and then de-excites. So this resonance scattering is most important at the neutrino energies between 300 MeV to up to 1 GeV or so. So
this is corresponding to the resonance width,
which is
300 to 1000 MeV.
no, the resonance width is a few MeV. Okay, I should call it few MeV. It's not the resonance width, though there is some relation between them. But what I am saying is that it's a probabilistic process about how much energy is transferred from neutrino to the proton. So, a 300 MeV neutrino can excite the delta resonance provided it transfers almost all of its energy to the proton. But that will not be very probable. Whereas a 1000 MeV neutrino, it can easily transfer 300 MeV to the proton and still retain 700 MeV energy. So that's how you should view it. Now, this 1000 MeV I have mentioned because of what is coming next. But I'm just stating it that, and also delta is not the only resonance. There are other resonances, and that also we need to worry about. As you said, the resonance width does play a role, but more important aspect is how much of the energy is being transferred from the neutrino to the proton. That is the more dominant thing. And the next important thing is deep inelastic scattering, and this tends to dominate for neutrino energies greater than 1 GeV. So I said for neutrino energy of 200 MeV, the de Broglie wavelength is about 1 Fermi. So if you have neutrino energy 1000 GeV, the de Broglie wavelength is 1/5, which means it can really probe what is inside the proton. And the picture we have is that proton and neutron consist of massless subcomponents which we call partons. Sometimes they is also called quark partons. That's a different story. We will discuss that in the next lecture. But the basic point is that the neutrino, instead of interacting with the proton or neutron, it is directly interacting with this component of proton and neutron and transferring energy to this component. And in doing so, it is pushing this component out of the proton and breaking up the proton. Which means that we have to worry about the so-called strong interaction dynamics, which is a very complicated issue. But what effectively happens is you have proton or neutron going to where this X is a multi-particle final state. By the way, this is one of the tricky issues in describing deep inelastic scattering. So the basic picture sounds quite simple, which I have already described, that the de Broglie wavelength of the neutrino becomes so small that it is interacting directly with the components of the proton. And in fact, it transfers so much energy to one particular component that it pushes that component out of the proton. That is okay. But does it mean I see the component of the proton that the neutrino pushed out? Answer is no. Why is that? That brings in various aspects of strong interaction dynamics. This is and there is a concept involved called confinement, which says that the components of proton and neutron cannot be seen. What we can see are only mesons and baryons. This is a hypothesis, and there is a tremendous amount of effort being put in to theoretically justify this hypothesis. There is a lot of progress, but as far as I know, there are also a lot of questions. But as far as we know, nobody has ever seen a component of a proton or neutron. We have seen only pions and baryons. So the concept of confinement seems to be true. And if you apply that concept of confinement, all these subcomponents of proton, which are now broken up, they somehow find other subcomponents and appear in the detector as pions and baryons, which is what makes this X a multiparticle state. So, as far as neutrino interactions are concerned, we will consider three possibilities. Possibility 1, final state consists of electron and a nucleon. Possibility 2, final state consists of electron, a nucleon and a pion. If not pion, maybe a meson. It can be a K. No, it can't be a kaon. Making it a kaon makes things more complicated. So let's keep it a pion. A lepton, nucleon and a pion. Third possibility is, so first case we call it elastic or quasi-elastic. Second case we call it resonance. And third case where we have final state consists of a lepton and a multiparticle state. That is what we call deep inelastic. And by the way, if it is a neutral current, if it is nu L bar, then it will be L plus X. And in the case of neutral current, by the way, this was the reaction people used to actually observe weak neutral currents, because when electroweak model predicted that there is something called weak neutral current, how can you observe weak neutral currents when if there is both a photon exchange and a Z exchange? The photon exchange diagram will dominate so badly over the Z exchange that the possibility of seeing a Z exchange diagram is practically zero. But so you consider a case where there is no photon exchange, which means your probe is a neutrino. But with neutrino, this reaction was seen. But idea was to look for this. So you should see a multiparticle final state, but mixed up in that multiparticle final state, we should not see a charged lepton. And you try to measure the energies of the multiparticle final state as much as possible and try to estimate the energy taken away by the neutrino and make sure the kinematics works out properly. So this muon less deep inelastic, of course, accelerators had mu beam. So the final state here will be a muon plus a multi-state particle, and they looked for events of multi-particle final state but without muon, and that is how the neutral currents are discovered. And the deep inelastic scattering, again we can understand quantitatively because a whole formalism was set up to understand this deep inelastic scattering, and using that formalism along with electroweak model, we can calculate the cross sections for deep inelastic scattering. So for energies above 1 GeV, again we can do calculations, we can do measurements, and there is a good match. Energies below 2 GeV also, using electroweak theory, we can do calculations. But between 200 MeV to 1 GeV, where the resonance scattering dominates, that is where we have a problem. Unfortunately, as far as accelerator neutrinos are concerned and atmospheric neutrinos are concerned, large number of our events occur in that energy range. So the theoretical computation and comparing it with experiment is a tricky issue. What's the time? 11:30. Okay, I will take about 15 minutes more and discuss some of the tricky issues related to the resonance scattering. Okay, now let us imagine we are in a accelerator experiment. We have a neutrino of energy E nu coming in and hitting a stationary target. But strictly speaking, we don't know what the energy of the neutrino is, because the accelerator produces neutrinos of varying different energies, despite the best efforts you can make. But if it is a quasi-elastic scattering, then neutrino, it comes and interacts with a neutron. It produces a mu minus and a proton, but typically that proton is non-relativistic and you can't quite often you don't see it in the detector. But I know the direction here and I can measure this angle. So my measured quantities are E mu and theta mu. Assuming that the original neutrino direction is the z-axis. But using energy momentum conservation and the fact that the proton that is produced is on mass shell, I can work out E nu as a function of E mu and theta. So that way, accelerator experimental people, they really love these quasi-elastic events because they can reconstruct the neutrino energy quite accurately. And of course, for them, L is fixed. So they know E, they know L. So they can do the L by E analysis very well. But in a atmospheric neutrino experiment, I don't know the initial neutrino direction. And if I can't see the proton, I can't really reconstruct E nu. So I have to depend on Monte Carlo that given the E nu theta nu distributions Monte Carlo gives, I put that in another Monte Carlo and work out the E mu and theta mu distributions. So because of which in that sense, the atmospheric neutrinos, they are at a disadvantage compared to accelerator neutrinos. Advantage, of course, is you have a wide range of E nu and a wide range of theta nu. So you use that to build up your advantage and try to control things. But because of this reason, the atmospheric neutrinos are at a disadvantage. And But if you go to higher energies, then in addition to muon, you are also producing pions. So if you are doing in T2K experiment, for example, the flux peaks at around 700 MeV. So there actually the quasi-elastic and resonance, they tend to compete, the two cross sections. So you should design the detector so that you can catch the pions also as much as possible. So that is one issue. But there is a bigger issue which is related to our ability to measure CP violation and mass hierarchy, etc. Because in accelerator experiments, you have mu E interacting with a neutron producing a proton and an electron, and you want to detect the electron. But this electron is quite high energy, 500 MeV to 800 MeV, maybe even higher if the neutrino energy is higher. But the electron produces an electromagnetic shower. But we can also have, here of course a mu is oscillating into a mu E and producing that. But I can also have a mu producing, going into a neutron or this can be proton also. This is also a possibility. And this pi naught decays into 2 photons. And the 2 photons, they produce electromagnetic showers. And if the pi naught energy is high enough, I cannot distinguish the 2 electromagnetic showers. It looks like a single electromagnetic shower. And I would think that's an electron. Mu to mu E oscillation is proportional to sine square 2 theta 1 3, which is a small quantity. So this oscillation probability is small. Whereas remaining mu probability is 50%. 50% will go to nu tau, but remaining mu is 50%. And even if this cross section is only some 10% of this, the production of electrons and the production of pi naughts, they will compete. So this is one of the biggest headaches accelerator neutrino experiments have. How to suppress the neutral current single pi naught production, because that causes a huge background to the signal you are looking for. So every experiment, wherever there is a problem, people produce 10 solutions, and of course you have to see which solution works better. So T2K, it pursued one kind of solution, which is essentially based on kinematics, and NOVA produced a different kind of solution, which is based on sort of making a lot of effort in reconstruction of the pi naughts and trying to build a more granular detector. And so it's going on, and I think right now, for example, the data of T2K and NOVA disagree with each other as far as this mu to mu E oscillation is concerned. So where is the disagreement coming from? Is it because of backgrounds are not properly understood, or is it because there is actually some new physics which is affecting nova in a one way and T2K in a different way? Right now, the disagreement is, one can wave your hands and say that okay, using statistics, I can. The disagreement is statistically not so significant that I need to worry about. But on the other hand, it is serious enough that we need to pay attention. And almost 2 years ago, this disagreement actually came to light 2 years ago. In fact, Nizam and I and a couple of students from IIT, we did some work on it. So 2 years ago, T2K and Nova said they have set up a joint working group to try to resolve it. But so far, I have not heard of any statement from that oh, this is the reason for the disagreement. So it is still something that people are working on. And as far as I see, this reaction is one of the big culprits. So, okay, basic point I want to emphasize is these resonance reactions. They are sitting bang in the kinematic region, which is of great interest to neutrino oscillation experiments, and they are the most difficult to model theoretically and also quite difficult to measure experimentally. And that is where all the experiments and all the theoretical modeling, they spend most of their time trying to understand that. Okay, I will stop now, and in the next class, which will be some 3 or 4 weeks later, I will start the formal discussion of deep inelastic scattering. Okay.
This connection between this resonance width and
Mm.
till what is it like? I feel like it feels like more the resonance width. I mean, broader the
That I agree, but the more important issue is how
the energy
the
is.
energy is being transferred. So,
One more question about this virtual particle.
mm,
So if the resonance width is more and more,
mm,
it's sort of like more and more virtual particle, right? Especially if it sort of overlaps into the.
mm, yeah. I mean, the resonance with, this delta, etc., they are broad resonances. So, and broad resonance means width is large, which means lifetime is small. Whereas there are very narrow resonances. For example, J-psi is one such example, where the width is very small compared to delta, etc. So they are relatively long lived, and we understand why J-psi is relatively long lived compared to this delta, because J-psi, the quantum numbers are such that it has to decay. The strong decay of J-psi is into 3-particle final state. It cannot be a 2-particle final state. Whereas delta can decay through strong interactions to 2-particle final state. So that's why the resonance width is broad. So if the resonance width is very broad, it means that I mean, see, there are two issues. The resonance width depends on the strength of the interaction and on the number of final states available. But if the strength of the interaction is fixed, instead of two final states, you have, instead of one final state, if you have two final states, okay, resonance width may be twice or 1.5 times twice. Okay, if you have 100 final states, but typically 100 final states will not have the same decay width. Only typically 2 or 3 will dominate. So the resonance width is determined by that. So once you determine what kind of interaction is leading to the decay, you can't change the resonance width by more than a factor of 2 or 3. So it is the strength of the interaction which determines the resonance width. So if you have delta with the resonance width, off the top of my head, I don't know the resonance width of delta, but let's say 200 MeV. You can't have a nearby resonance. You can't have another resonance similar to delta with the resonance width of 1 GeV. Because you are saying the resonances are decaying due to strong interactions, and that strong interaction strength is setting a limit to what the resonance width will be. Instead of 200 MeV, it can be 300 MeV. It can't be 500, 600 MeV.
But you had about virtual particles. You had said that.
No, don't call them virtual particles. They are resonances.
Okay. Okay. Let's talk about this off-Marshall.
Okay. Yeah.
Which
What?
is called virtual particle.
Right.
So there, we don't have that E square minus B square equals M square. That
Right.
equation doesn't hold.
Yeah.
If you look at resonances also, it doesn't hold exactly, right? It holds with a.
It holds up to the resonance width. So E square minus P square is M square plus gamma square by 4.
So that sort of makes it the definition. I mean, that kind of equates resonances and off-Marshall particles, right?
Yeah, I mean, okay, you can. Let me put it this way: we are not doing mathematics here. I mean, for a mathematician, 10 power minus 100 is not 0. But in physics, we take 10 power, quite often we put 10 power minus 10 also as 0. So, in that sense, I mean, how much off-Marshall things are, that depends on the two parameters, M and gamma. What is the value of E square minus P square minus M square? We say if it is equal to 0, we say it is on Marshall. If it is not equal to 0, that is off Marshall. But that's a slightly hand-waving definition. A more precise definition is E square minus P square minus M square. Is it less than gamma square by 4? Yes, we say it is on Marshall. Greater than gamma square by 4, then it is more likely to be off Marshall. That is how we define things.
You are saying that electromagnetic interactions of neutrinos. So is that due to higher order Feynman diagrams?
Yeah.
The W boson emits photon.
Right. Both the neutrino emits a W and becomes a charged electron, reabsorbs it. So in the internal loop, there is a W as well as a charged electron. both of which can couple to photon, and that leads not to electromagnetic charge, not electric charge, but magnetic moment.
That gives the neutrino a magnetic.
That gives a magnetic moment to neutrino. I mean, recently there was a lot of excitement about the precise measurement of muon magnetic moment. So the first famous calculation was done by Schwinger, who calculated the one loop correction to electron electromagnetic moment and calculated it to be a finite quantity, number one, and found the answer to be alpha by pi. That is one loop correction. Then people did 2 loop, 3 loop, 4 loop corrections, and theory and experiment match up to 4 loop corrections. But when people tried it with muon, there is a mismatch, and the new measurement says yes, the mismatch is still there. What is the reason for mismatch? We don't know.
So here, can we identify the second process from some other decay modes of pi 0? Though they are not.
No. Pi 0 decays into 2 photons. The other possibility is E plus E minus, which is equally bad. But the branching ratio of pi naught to E plus E minus, I don't know, it's 10 to the minus 4 or something. So, yeah, if it's the decays of pi naught limit us. Just imagine if this is a higher energy process, and instead of pi naught, this is a k naught. K naught has lot of decay modes, and I can easily identify a k naught. But pi naught that way is a very troublesome particle as far as neutrino physics is concerned.